Didn't get time to read another paper, so I just finished the part that I haven't finished last time. Yeah, this is the CQ lookup for part 2. I think most of you will forget the parts that we are talking about for the part 1, so let's just do a recap for the part 1 for the most important part. What CQ or what lookup want to try to resolve the problem is that we have a F table and we want to know if F belongs to T. So yeah, F is in this F N and T in this F capital N, and N will be smaller than capital N. So we try to figure out if F belongs to N. For CQ, there is a, I think it's a lemma to figure out that is if you can prove this X plus Ti mi equals to some n x I for I 1. So this, you can prove this if they are equal. So let's give an example for that, such as for T, it normally will be a large table. We just use a simple vector 1, 2, 3, 4, 5. F will be can be multi-site, so you can have the same numbers for that.
Here is I.
Yeah, right. It's I. Thanks for that. This is better? Okay. Say I want to demonstrate this F belongs to T. You can see from this. So T has all the numbers in F. So here you just can say that, but we will demonstrate how to use this equation to prove that. So M is the numbers that T elements shows in F. So M1 here will be, but there are 3 1s, so M1 will be 3. M2 equals to 1 because there is only 1 in T. And M3 there is no 3, so M3 equals to 0. M4 will be 2. M5 will be 1. Okay, we just sum them together. So the left hand side will be X plus 1. M will be 3. Then X2, 1. Then X3, 0. X4, 2. X5, 1. Then we do the right hand side will be all right. Right. This is good. Okay. Same x1 is 1. We just x1, there are 3 x1, right? 1, 1, 1. And these 2, 4, 4, then 5. Yeah, actually they are the same, right? So this is here, and here is here. So yeah, this is 0, 4, 4. There are 2, 5, 5. So they are the same. And so with this equation, you can prove that if this equation they are the same, then you can say f belongs to T. So if you, so normally we'll convert this problem as a polynomial. So we'll define this one as AI, this one as a BI. So we can convert this problem as a AX for this part, AX equals to, so before that, verifier will send a random number to replace this X. Verifier give a random number beta. So it will be AI equals to beta at Ti mi. So this polynomial will be AX equals to mx beta. We just replace the I with the polynomial Tx. And this one will be Bi equals to beta at Fi 1. So Bx equals to beta at Fx 1. So we will reduce this problem to 3 checks. The first one is Ax is correct. Second one is Bx is correct. And third one is the sum check. They are the same. Yeah, so that's the main idea for this CQ. And for today's sharing, I will not go through all these checks. We only focus the part 2, which is how to achieve the complexity with the plural side is O n log n. So n is this n. And with pre-processing, O n capital N log n. For this part, we only talk about how to optimize this one. Okay. So from this part, we can see Ax times beta add Ax times Tx minus Mx equals 0. But this only satisfied when x equals to f capital N, right? So normally we want to prove this on the entire finite field, so we'll just make it as this form: q a x z v x. I will not explain this part because we already have several sessions to talk about this. So we can convert this a x t x we will pay attention to this part equals to q x Okay, so when we verify that, you need to do the pairing e a x t x equals to e q a x z x e mx minus beta ax. Right. So far, any question? Yeah, so we need to optimize this part. How to optimize? So now we have this equation. Then we will say that ax, we can use Lagrange polynomial to, you will have this equation x to n li x ai. Let me check. Oh yeah, we want to calculate this one. Ax tx equals to lix ai times tx, and we for this part we have lix tx minus ti equals to 0. And then we can do the similar thing here. It's just make it as q, this is a qt, or just use qi because everyone is qi, qix times zvx. So let's put them together. Lix tx equals to qix times zvx. We just move them this side will equal to lix ti. So this part is this part and this part. So we'll do this calculation here. AI times QIX JVX at X TI. All right. Continue to do the calculation. AI QIX JVX AI LIX TI. Yeah, I think if we compare this one with this one, you will see that this is JVX, this is JVX. So we can say that QAX will be this one. So normally if you calculate this one, there will be higher complexity. But for this one, actually, if AI, if you know that AI is in I think the paper says that AI equals to 0 if I not belong to N, because A is some sparse polynomial or sparse matrix, if I'm not wrong. So this calculation can be reduced to N log N. I don't know if I'm right. It is then we have this one. So there's a way to do the optimization in the processing stage. We know that LIX TX minus TI equals QIX JVX. So QIX will equal to TX minus TI divided by JVX LIX. LIX right. So here LIX equals to JVX JVX derivative, this one is, then is XGI. So this is the,
Here is the
yeah, GI, yeah, right. Yeah, this is the Lagrange form. So we put this one here, you will get Tx minus Ti. So this one will be vanished. And here will be JV derivative GI x minus GI. And it equals to, we just move this part here, Tx Ti JV GI. Yeah, for this part, it's just we can name it Ki. And this part can be the complexity. If you calculate this one as a polynomial, it will be n log n with some, I think paper called it some KR method. I have no idea how they do this one. Is that there are two names for combine them to calculate this. Let me check. Yeah. Oh, is it called Faced FK Tom?
Oh,
FK Tom. Oh, sorry for that. FK Tom. I don't know how it works, but it can reduce this one to Ki. But how about for this one? We can calculate it with because JV x equals to x n minus 1, if we choose V as a multiplicative subgroup, then JV derivative will be nx n minus 1. Then JV derivative will be, this one is GI, so GI. No, this one is not finished. Because we know x n equals to 1, right? So this one will be x will be this one. Then this one will be GI, and so this guy will become to GIN. You can treat it as a constant, so you can only need to take care of this part. So this part will be n log n. And the Ti, all the Ts you know beforehand, so you can do the calculation for Qix for T in the pre-processing stage. Yeah, so I think that's the part for the optimization. All right.